Squeeze lemon juice onto baking soda, and you get an immediate fizz. That reaction is a chemical process playing out on your kitchen counter. To figure out what is happening inside those bubbles, you need a specific set of tools. This flowchart maps out the scientific method. You start with an observation. You see the mixture bubbling. Next, you form a hypothesis, a testable guess that the acid is reacting with the base. Then, you design an experiment, mixing specific amounts to see if that guess holds up. The cycle continues with analysis, where you measure the results and identify the gas produced. That leads to a conclusion, confirming a chemical reaction took place. But the final step on this chart loops right back to the beginning. A single experiment does not provide absolute proof. Instead, every conclusion spawns a more precise question. Science is a continuous loop of inquiry, driven by our desire to understand the world. We can apply that same toolkit to track how everyday materials transform when we add heat. An ice cube on a warm table melts into a liquid puddle, while a lit wax candle slowly burns down until it disappears. Both are reacting to heat, but they are undergoing two different processes. On the left side of this diagram is a physical change. The H2O molecules in the ice simply loosen their structure to become liquid water. You can reverse this by putting the puddle back in the freezer. On the right, the burning candle is a chemical change. The heat breaks the wax molecules apart, forcing them to bond with oxygen to create entirely new substances, smoke and ash. Identifying exactly how the internal structure of a material shifts allows us to predict its behavior and determine if a change can be reversed. Sometimes the change happening inside a material is invisible to the eye, like the energy moving through an active electrical circuit. To make a simple lamp glow, you need three physical components: a power source like a battery, conductive wires to provide a path, and a switch for the flow. This diagram compares an electrical circuit to a municipal plumbing system. It helps clarify the difference between voltage and current. Think of voltage as the water pressure. It is the force pushing the energy forward. Current is the actual volume of flowing electrons doing the work. By increasing the pressure at the battery, you drive a higher volume of electrons through the system. Controlling this flow of electrons allows us to take raw materials and build the circuits that power modern technology. If we zoom out from a small circuit to the scale of the entire Earth, we find a massive energy system driven by heat from the sun. Solar energy drives the global water cycle. The sun's heat causes the water to evaporate from the oceans. As it rises, it cools and becomes condensation, eventually falling back to the ground as precipitation. That same solar energy powers biological life through photosynthesis, the process plants use to capture sunlight and turn it into food. This chart tracks the inputs and outputs. The plant absorbs sunlight, pulling in water and carbon dioxide. It uses that solar energy to manufacture glucose for growth, releasing oxygen as a byproduct. Animals and humans rely on respiration. By consuming the plant's glucose and breathing in its oxygen, they generate energy. In return, they exhale carbon dioxide back to the plant. This exchange keeps the levels of oxygen and carbon dioxide in the atmosphere stable. It is a self-regulating cycle that supports both plants and animals. We can scale our observations even further, moving from the Earth's surface to the mechanics of the solar system. It starts with the casting of a shadow. Early humans noticed that shadows shifted predictably throughout the day. By placing a stick in the ground and tracking those shadows, they invented the sundial to measure the Earth's rotation. That rotation on its axis creates our daily cycle of day and night. At the same time, the Earth is making a continuous orbit around the sun, which creates our yearly seasons. The moon's orbit adds another layer. Just like objects on Earth, planets and moons cast shadows across space, creating the lunar phases we see. By measuring shadow lengths at different locations, early observers were able to calculate the curvature of the Earth and the tilt of its axis. This geometry is what allows us to predict seasonal changes and planetary movements with mathematical precision. A solar eclipse occurs when the moon aligns between the sun and our planet, momentarily blocking the visible light spectrum. Because the sky goes dark during an eclipse, it's easy to assume it is safe to look with the naked eye. This eye schematic shows the danger. While visible light is blocked, invisible high-energy UV radiation pours around the moon. It enters your pupil and focuses sharply onto the retina, acting exactly like a magnifying glass in the sun. Because your retina lacks pain receptors, you will not feel this radiation burning the tissue. This causes permanent damage without any immediate sensation, which is why specialized protective lenses are required. Whether observing lens juice in a kitchen or tracking radiation in space, the scientific method provides a consistent framework. It is how we turn curiosity into the reliable data needed to navigate the physical world.